seems there are two different directions in. All right, if you look at the papers on the big path algebras, and there are many now, 100, 120, I guess, on archive. There are two different themes or two different directions that you can see. One is that the theorems of this type of theorems, so in the graph, then the big path algebra has property so P if and only if E is of the form so you can see a lot of papers of this type that you choose your favorite adjective and you put it here. So P could be simple, and then you wonder what sort of graphs would produce that type of graphs. Oh, sorry. What sort of graphs would produce that type of algebras? And just the magic of these relations of CK1 and CK2 are that you oftentimes get some properties on the graph, and they are if and only if. So you put simple, you get you put here Noetherian, or any adjective from ring theory, and you get some criteria on the graph E. The other one is that classification of the big path algebra. And that means if I hand you two graphs, E and F, would you be able to tell me if the big path algebras associated to these graphs are the same or not? So as you saw, the graphs could look very different, but the big path algebras would be the same. So here, this graph would be just one vertex and two loops, and here it would be two vertices and this graph. But when you basically hit this with the lead, then you would get the same thing. So can you come up with some sort of an invariant that very quickly would tell you that the big path algebras are the same? So is it possible to have some invariant that if these are the same and this invariant should be somehow easy to compute, then you would say yes, then the big path algebras are the same. And as you know, there is a parallel story on C-star algebra. So you have graph C-star algebras, and there the K0 and K1, these functors, have been very successful. In fact, they would classify graph C-star algebras completely. So people thought, because the behavior seems to be very similar, people thought maybe K0, Grothendieck group, would classify the big path algebras also. So let's have a look at the Grothendieck group, and I'm going to remind you what Grothendieck group of a ring is. Muge mentioned that, but just let's go through this again. And then I would try to apply Grothendieck group on the big path algebra and see if I get a complete classification. All right, so just remind you of the Grothendieck group of the ring. So let me just do this in general first. So you start with the monoid. And what this means is that you have a set and you have a binary operation. And when you add the elements, of course, you end up in V again. And then if you put three elements here, then it doesn't matter if you read it from right or if you read it from left. So if you read it from left or if you read it from right, you end up with the same result. And then I also need to have, okay, in my situation, I want to have an abelian monoid because the K0s are going to be abelian. And then there is also a zero element that doesn't basically push A to any different places. So these are the assumptions for a set being a monoid. So now as soon as you have this monoid, there is a way to attach a group to this. So I can construct a group in a universal manner. And it's called the group completion or enveloping group of V. And you might recall, Mugi mentioned this, that this group completion, G, has this property. First of all, you have a homomorphism from V to G. And oftentimes this V does not sit inside G, it is just a homomorphism. And this kind of smallest homomorphism. Namely, if you have another group H and another homomorphism here, then you have a unique homomorphism going from G to H. And that reinforces that this G being unique of the isomorphism. So now how would you construct this G? And then, well, the natural example is that you have this N, this is a monoid, i.e. you don't have inverses, so 2 does not have any inverse. But if you construct that, sorry, if you construct the monoid, if you construct that group, it's going to be Z. And here in this case, N sits in Z, but oftentimes it doesn't. So oftentimes this is not injective. In fact, you have a criteria when this would be an injective map. So I'll mention that. Okay, so how would you construct this G? So you look at V times V, the Cartesian product of two copies of V, and then you force that these two are the same if, so let me just write it here. The definition is that M1 plus N2 plus some Z would be N1 plus N2 plus Z. Okay, and then you would check that this is the equivalence relation, and it respects the addition of the monoid, and that would be a group. So this needs to be checked. For example, here you would see easily that for any M plus M place the 0. You place the 0 element of the monoid. You can check that quickly. All right, and then
Excuse me. Here Z can vary over the for M.
Z is in
Fixed.
V.
Fixed.
No, it's not fixed. For any of these tuples, you need to find just one Z. And then, well, you have a homomorphism that's very easy to guess at least. That V goes to V0, and that gives you a homomorphism. Here is a monoid, here is a group, and this group has this property here. So now, let's look at some examples. You have seen this example here, that this is the monoid, and the group is much, much bigger. And one thing that's always the case, because V plus starts with V times V, so it's much bigger. But this is not always the case. So let me give you an example that, in fact, this V plus shrinks. In fact, sometimes it would be even 0. So, example, and we can check this maybe in tutorial, that these claims are correct. So I'm going to start with V, Z, and then I'm going to add just one element star to this Z. And here now I have to give you the addition. So inside Z, you know how to add. If you have star plus star, I just put star, and anything else plus star, I put N. This is also a monoid now. And you would be able to check that V plus is in fact Z. So although you go through this process and it becomes a much bigger set, but when you collapse these, you would end up with Z, so it gets kind of small. So example 1, we need to check this. We can do it maybe over the tutorial. And then the second one is if V has a 0 element. And what I mean here is that for any v, so there is a 0 in, maybe I call it again star in v, such that v plus star would be star. So that's what I mean by 0 element. Like it's behaving like multiplication. So v plus the star, it always gives you star. Okay. Then the group completion is in fact a 0. And then the last thing is, right, look, example 3, or maybe even a theorem. So you have B sitting in B plus. So now, so there is a homomorphism from V to V plus. Then V, this phi, is injective. It's all complex. Okay, so now you have this map, and then phi is injective if and only if V is a cancelative monoid. So i.e., that means that if you have V plus some m is equal to V1 plus some m is equal to V2 plus some m, then we are very comfortable in group theory, you can cancel m, but we are working over monoid, so you don't have inverses there, so you cannot just cancel. But if it happens that these two elements are the same, and then you would conclude that this is the same as this one, this is called cancelative monoid. So if this happens, then you can prove, in fact it's not very difficult, that this is an injective map. It's an if and only if condition. And if you compare this, you see that if your monoid has some sort of cancelative property, or close to being cancelative, then this is a much bigger group. But here you see it's highly non-cancelative, right? And then therefore this collapses to be 0. So more you would be able to cancel things, that gets closer to being injective.
How does phi act? How does what's the act?
Oh, this is just V goes to V0. This is this map here. All right, so now let's move to actually rings. So I have the tools. So for any monoid, I have this group. So I'm going to construct a monoid coming out of a ring and then plug it into this machinery. So now A is a ring, and I really want here 1 to be inside A. So if your ring does not have identity, then you have to work a bit harder and then construct K0 going via idempotent. So I don't want to do that. So your ring has an identity. Then the monoid you consider here, the monoid you attach to your ring A is this one. So you look at all the finitely generated projective modules over A, And you get the isomorphism classes of that. So you pick one finitely generated projective modules, and you look at all the modules, all the projective modules which is isomorphic to this one. So you look at that as one element. And then you might guess what would be the addition here. How should I define the addition here? So can you tell me what should I put here? So if you have two projective modules, how should I assign a new one to it? Just using a direct sum. So this is, again, not very difficult to check that if these two are projective, the sum is also projective. And that gives you a monoid. So zero module is projective, and it behaves like zero. So that's one reason I get the class isomorphism classes of P. Look, of course, this P plus 0 is not P, but it's isomorphic to P. So in the class, they are the same element. So the famous sort of example is that if F is a field, then the monoid assigned to this F is N. So let's look at this one. Why is that? So now, I fix the field F. Now I need to look at all the finitely generated projective modules. So now just let's look at any module. So F, a module over F. And I think this is one of the first theorem we prove in linear algebras, that any module you get over a field, it has a basis. All right. And if you look at the proof, in fact I was looking at it recently, is that you explicitly use the fact that each element here, which is not zero, has an inverse. So you use that fact to prove that this has a basis. So because M has a basis, then M is a free module. So any module you get, it's always free. Therefore, it's isomorphic to some Fn. The next thing you prove is that that basis that you come up with for M has a unique cardinality, sort of an IBM property. So if Fn would be isomorphic to Fm, then N is the same as M. All right. Good. So now, going back here, I have to pick up the finitely generated projective modules, but I know any module is free. So my options are F and the isomorphism classes of that, F2, the isomorphism classes, and I know that F2 and F are not isomorphic because of that, and you keep going. And then therefore, this is an indication that E of F is N. So this is F, this is 2 times F, this is 3 times F, and so on. So now, this monoid really tells you if you have an IBN or not. So if it happens that AN would be isomorphic to AM, in here, N copies of A would be the same as M copies of A. And it detects that the A has an IBN or not. In fact, this is kind of a very weird property if you think about it. Look, if A happens to be isomorphic to A cubed, and here, remember, these are when I'm saying that as an A module, of course, left or right. What does this mean? This means that, in a way, here, if you're in this space, so you're walking on a line, right? So you're walking in a one-dimensional thing, so you're actually walking on this line. But somehow, if you just look differently, you see that as you are moving here, somehow you're at the same time moving in a three-dimensional space, and that's kind of weird, right? But that happens if A is very far from a field. So if this happens, that means you cannot really do that much linear algebra. All right. So I have K0 now, which is the completion of V. So let me just write it down. So definition of the Grothendieck group. Here again, A is a ring. 1 is in A. Then the definition of K0 of A is I look at this monoid and I do the completion. And right away, then I have K0 of a field is Z. And because of this property, if you would see torsion here, so if you have a ring and this has torsion, that's kind of an indication that you are getting away from linear algebra. All right. So now the question is, can I use K0 to classify the Leavitt path algebras? Can I say that if you have two fields E and F, two graphs, then can I write something like this? So K0 of L of E is isomorphic to K0 of L of F. Can I do this? And if you recall, Muge showed you the computation, how you compute the K0 of L of E, and it was very easy. So you can easily compute the group assigned to this LE. And can I write this, that if they are the same, then the Leavitt path algebras has to be the same. Okay, so we are going to look at that. But before this, let me just show you the cases that actually K0 would classify rings. So there are cases that K0 is a complete invariant. K0 classifies the rings called ultramatricial algebras. So let me just remind you what is an ultramatricial algebra, because as it happens, if you are working with the Leavitt path algebra, remember this has a Z gradient. If you look at the zero component, this is an ultramatricial algebra, so it behaves very nicely. So what are the ultramatricial algebras? In fact, the construction is extremely easy. So ultramatricial algebras, you'll see in 2 seconds how easy it is to construct an ultramatricial algebras. But it falls into that sort of behavior that you start with something simple, but if you repeat it a lot, you get some complex system. So this is one of those examples. So first of all, I have to tell you what is a matricial algebra. So definition, fix a field F. Okay, I'm just going to write a bit informally. Is a matrix is called a matricial algebra. So you pick your field and you look at the sort of a Cartesian, finite Cartesian product of matrices over that specific field F. And that gives you what we call matricial algebras. In fact, you can call it also semi-simple rings. Okay, but let's stick to the notation of matricial algebras. Okay, and now, what is an ultramatricial algebra? So a ring R is called ultramatricial if R is a union of Ri, where R1, so this is 1 to infinity, R1 is sitting inside R2, sitting inside R3, and Ri's are matricial. So I look at a chain of matricial algebras sitting inside each other, and I get the union. Pretty easy. So I remember the first time I saw the definition, I thought, well, this is very easy, I understand it. And then when you start working with it, you see how complex it is, how complex these algebras are. So let me give you an example. So what I really need here is that when I say this ring R1 is sitting inside the ring R2, I want the identities match. So if you
I
think
have a
about...
question. So matricial algebras you define for field only, right?
Yes, so you fix your field F. That's very important.
No, but when you are saying these RIs are matricial, then
That's right. So the field F is fixed. So I would say Ri are matricial algebras over fixed field F. Does that make sense? So I don't want to say you can extend your field, but I don't want to do that because then the classification fails. So the other way you can think about this is that R1, there is an injective map from R1 to R2, and this is sends identity to identity, R3, and then I get the direct limit of that. Okay, let me give you an example how this works. Example. So just fix the field F. This is a matricial algebra. This is just a matricial algebra, looks like this. Okay. And then this sits inside M2 of F. So I need to send an element here, two copies sitting on diagonal. Then M2 of F is sitting inside M4 of F, and you got the idea how to continue. So I send it to diagonals. And then I get the union of this. So my ring R is a union of this M2n of F, n from 0 to infinity. Is an ultramatricial algebra. And again, back to your question, of course I could put here any ring R and just do the same thing. I could put here F, and this could be a bigger field. I can do all that, and you get a ring. But then I cannot do the classification that I'm going to write there. All right, so again, this is pretty simple, but let's do one a bit more complicated. So I start with F times F. So here, again, it's a matricial algebra, F times F. Then I push it to, let me just make sure that I give you the F times M2 of F. Then I'm going to push it to M2 of F times M3 of F. So now I have to tell you the maps. All right. So get F1 and F2, and this is how I'm going to mix and match and shuffle things around. So I'm going to put F2 in the first component, so that F2 comes here, and then here I put F1 and F2. And if I repeat this process, do you agree that I would end up here? So if I get an element here, and I get an element here, I'm going to put this element in the first component. Good. So now, if I have 2, I'm going to put this element in the first component, and I'm going to put this one here and this one here, so I end up in M3 of F, so it matches. Okay, so and then you get the union of this, and you get an algebra, whatever that is, it's an ultramatricial algebra. So now, there is a nice way to attach some sort of a graph to this. They are not directed graphs, and they are called Roozbeh diagrams. Just describing this, so let me just show you that. Here, you start with one field F. Here also you have just one component, so I put one vertex here. Here also you have one. So this one vertex means that I have only one component. So here you have two. So I just, in this, the second Roozbeh diagram, I have two F's, I put two. Here I have two. Here I have two.
With the Fibonacci.
Yeah, you're right, actually. Here it would be Fibonacci, so yeah. Okay. So now, going back to the first one, look, I go from F and I put two copies here. So I just go like this. So that indicates that I start with this and I put two copies in the next level. And I'm doing the same thing here. So I just put and I continue. So let's try the second one, that makes it more clear. So I have F and F, that's the first F, that's the second F. Maybe I can even write here F, F. And then here I have F and two of F. Now how would I mix these elements? So, you see F1, okay, let's look at F2 first. So F2 here, I push it to F1. Okay, so F2 goes to the first component. And then another component is going to the second one here. F1 is only going to the second one. So out of this, you're supposed to basically decipher this map. And I'm repeating the same thing again, so I guess. So this diagram is supposed to describe these maps here.
Are these diagrams only for used only for ultramatricial algebras?
What do you mean? They describe ultramatricial algebras. All right. Now, one thing you notice is that I do some pattern here, and I keep continuing the same pattern. Okay? This is called the stationary ultramatricial algebra, because I'm just keep repeating the same thing. But you don't have to. You can start from here, do some mixing, and then do something different here. All right? And then get the union. So what I'm trying to say is that you can start with one F, and then send it to F times F. I just get F, send it to two copies of F. And then I'm here, and this represents this one. Here I can do something different. I can do this. Here I can do this. And then mix and match, and now if you can imagine what sort of algebra I would get. So you can really construct very complex rings. And if you want, to see how complicated they are and in which places they appear, I encourage you to look at this survey of Vershik. It's called, it's a survey. And in the title it says locally semi-simple algebras. Because this is another name for ultramatricial algebras, because locally, at each stage, you are working with a semi-simple algebras. So,
May I ask another question? From interrupting, sorry. For a given collection of RIs, by using different Bratelli diagrams or the inclusion maps, will we be getting different ultramatricial algebras, although both of them are the union?
well, that's again a classification theorem. So you can come up with two different Bratelli diagrams.
Yes.
The algebras look different, but it is possible that they are isomorphic. So that's a classification. If I give you two different Bratelli diagrams, would you be able to tell me if they give me the same algebras? Exactly like the path algebra. And the answer is yes, you can. And that's using K0. oops, okay, so this locally semi-simple algebras, the survey, you see that it has connection with number theory in a very strong manner. It has connection with a lot of analysis and here and there, a lot of different subjects. All right. So let's look at K0. And let's look at one of these algebras, M3 of F. So what's the K0 of R? So I know that the K0 of F is Z just because you have linear algebra over fields. Now what is the K0 of matrices over a field? So you have this Morita theory that tells you that the category of modules over this matrix algebra really behaves the same as the category of modules over F. So you collect all the modules over this matrix algebra. You collect all the modules over F, and you see that there is an equivalence here. And I can tell you the explicit map. So if you look at a module over this, well, I have to assign something here. And this is how it goes. 3 copies of F. Now there is a map, there is a functor going backward, and then you have to compose them and you see that you get an identity. But this is an equivalence with this map. Therefore, it immediately tells me that you have an isomorphism in this level, and if I get, this is just one generator of this. So if I start with T, or here, did I do X? I just send it to X tensor F to the power of 3, or 3 copies of F, and that's the isomorphism map. It's an isomorphism. So, K0, so maybe I just write it there. So the K0 of this matrix algebra is in fact the same as K0 of F. So now, what do you think the K0 of 5 by 5 matrix over F would be? It's the same trick. So instead of 3, I just put 5, and here I take 5 copies of F, and you have an isomorphism, and this is Z. So, I mean, I keep saying K0 would classify these algebras, but already it fails in a very simple case. I mean, it doesn't see the dimension to start with, right? So, K0 in itself would not classify. So, but now, let me look at this. If you are working with the K0 of A, you have one specific element, the order unit. Mugi mentioned that, because A is a free over itself, so in particular it's projective, so I have this specific element inside K0 of A. So let's look at that. Sorry, let's look at that in this situation. So what is this element in K0? Well, okay, so I have K0 of M3 of K. I know this map will send this to K0 of F, and this is an isomorphism to Z. All right. So now, how does that go? It goes to look at this map here. So, can you tell me what I would get? Just plug it there instead of A. F, yeah, so I get M3 of F, tensor M3 of F, F3, but I know from modular theory that they cancel, so you get F, 3 copies of F. So, and it's represented by 3 here, so 3 copies of F is 3. So that gives you the clue. So, because then M5 of F in the next one goes to 5. So in order to do the classification, not only I need K0, I need to carry with me this order unit also. So I have to keep track of that. That gives me the dimension. Okay. But then, sorry, I think these two are enough for these matricial algebras, but when you go to the union, it's not enough, and that's the genius part of people who find this, that you need one more ingredient. So not only you need to carry with you this and this, you have to also carry with you the positive cone. So what is this one? So this is just the image of this map. So what I'm basically doing, I'm keep tracking of all the actual projective modules inside K0 of R. Just to look at the collection of projective modules here. And I call these a positive cone. Now, your complete invariance would be this triple. And here is the theorem. It's really a nice theorem. So theorem green so suppose A and B are ultra matricial F algebra. Again, going back to your question, look, when I construct here this, I could have started with another field F2, I don't know, L, right? And I do the exact same thing. And you get the exact same numbers here. So again, the K groups would not really distinguish between the fields you are working. So it could be a field with characteristic 2, or it would be a characteristic 0. You always get the same result. So I need to fix my field F. Okay, so these two ultramatricial algebras started with some fixed field F. Then A is isomorphic to B, in fact, as F algebras, if and only if the K0 of A happens to be isomorphic to K0s of B, and with that isomorphism, the positive part goes to the positive part, so pushes the projective image of projective modules to the image of projective modules. And if you apply that specific map to this element, it would go to B. So this is this statement. So K0 with a bit of more ingredients would actually classify ultramatricial algebras. It's really a nice theorem, and if you look at literature on this, you see these four lines I wrote here. It actually took about 50 years to be like this, okay? So it starts with a German mathematician Green in 40s, and I had a very quick look at this paper. You know, it's very difficult to read this 40s and 50s paper, and in fact it was in German. So he realized some sort of algebras and some sort of invariant he came up with. Then Bratteli, I think from Norway, in 70s, look at this paper, and then he comes up with these diagrams and classifies those. And then Elliott, I think in 80s, would look at this paper and then comes up with this definition of ultramatricial algebras, and the invariance he comes up with is based on idempotence. And then eventually, Goodall look at this paper and see that in fact, that idempotent things that Elliot is working with is in fact that K0. So it took like 50 years to write this paragraph the way it is now. All right, so this is really nice. So let's see if K0 would classify now Leavitt path algebras. Okay, so let's start with just one example. Let's look at this. So you have this graph E, and if you remember, you can tell exactly what's the Leavitt path algebra here. So you look at this thing, and you count all the paths ending here, and it would be the M3 of K. If your field is K. Can I put here F? Yeah. So the coefficient field is F. All right. And let's look at another. Let's look at this graph F. Let's construct its Leavitt path algebra. So the Leavitt path algebra is, again, the game was you remove one of these edges from the sink, you get an acyclic graph, as you see, and then count all the paths ending here, and that gives you M3, and then, because you have a cycle, you have to compensate that with a Laurent ring. So now let's try to classify these using K0. So the K0 of LE, K0 of LE plus and LE, then K0 of LF, it's positive cone, and this order unit is. Okay, this one, we have done it here. So you are in this situation. M3 of F. So I know this is Z. The projectives are going to a positive part. And this one, so M3 of F, goes to 3. So this is your invariant here, what you get. Now, how about this one here? So I'm working, sorry. So I'm working with matrices over a PID ring. So now I have to remind you, a PID ring, the projective modulus over a PID is free and has also a unique basis. Okay. So now that means you don't have projective modulus. You are just working with free modules. So pretty much like F. So M3 of F, again using Morita, I just have to worry about the Laurent case, and because the projective are free, here also you get Z, and M3 goes to 3 copies of this thing, so 3. So these are the same, exact same thing. But of course, this is not isomorphic to this one. For one thing, the center here is F, the center here is a Laurent ring, so these two are very, very different rings. So unfortunately, K0 would not classify all the Leavitt path algebras. So the conjecture, again, Muge mentioned that, and I think Brango also, is that, okay, so K0 would not classify all the Leavitt path algebras. What if I just look at one specific class of the Leavitt path algebras, and they are called purely infinite simple? So would K0 classify as purely infinite simple Leavitt path algebras, and that's all? Okay, so now, so remember that now I'm going to the graded case, so graded K theory. And if you recall, the graded K theory, the graded rings would capture more information, and I'm hoping that maybe the graded K theory would also capture more information and therefore would behave as an invariant. So if you recall here that in this case the usual algebras are isomorphic, but as soon as I look at the graded algebras, they are not isomorphic. Okay. So grading will carry more information. So that's why I'm going to imitate everything I've written so far, but in a graded setting. So just remind you that how do I define K0 of R? Well, I said that you look at the isomorphism class of all finitely generated projective modules. This is a monoid, and you just complete that. So how do I define the graded version? Well, it's very easy. You just plot graded anywhere you see. So the graded version is you look at the class of isomorphism class of P. P is finitely generated graded projective modules over R. And then you do the completion. That's it. So a couple of things I have to mention here. When I say here isomorphism classes of P, that means I get P, and if Q happens to be isomorphic to P, then they represent the same class. When I say here isomorphism classes of P, now I'm talking in a graded setting. So that means if P and Q are graded isomorphic, then they represent the same class. It is possible that P and Q are isomorphic, but not as a graded module, and they present different class. And that's where the power of K0 will come. Okay, it distinguishes a lot more. So it is possible you have two projective modules, they are isomorphic, but they are not graded isomorphic. Therefore, they have two distinguished graphs, two distinguished classes. Of course, you have this map, a forgetful map. Can you tell me why? That's right. Because we just proved that was a little theorem, we just stated that if you have a finite generated graded projective, it is projective. So I can just push it here. So you have forgetful map here. It's not subjective, it's not injective, it's just a map. Okay, now, a very important fact here is this. If P is finitely generated graded projective, then any shift that I apply to P is also finitely generated graded projective. So if you have a module P and it happens to be projective, if you shift it, it still stays projective. Then you just give me a proof. If P is finitely generated projective, that means it's some direct summand of AIs of this form. So that's one way to say that P is finitely generated graded projective. Now if I shift it, so I'm shifting all the modules at the same time. Well, that means that this is also a direct summand of A's. It's also finitely generated projective. So what does that tell you? That tells you that if I start from the beginning, let's go back. I start with this here, which was just the this set. Okay. Now, if I get an alpha, I can shift these and I look at P alpha. This is also in here. Right? If P is in here, then P alpha is in here. And it's not necessarily, if I shift P with alpha, it would be the same as P. This is not necessarily the case. So you might end up with a different element. All right? So that is an indication that in fact you have an action of gamma on, so if this gamma is a group, you have an action of gamma on this monoid. You just push monoid back and forth. So, and then when you do the completion, this action is reserved. So you have an action of gamma on the graded K0. You have to go through the definition and make sure that this action is preserved. Here, it's well defined and so on. So you have an action here. Another way to translate that, i.e., another way to say that the group acts on a abelian group is saying that K0 graded of R is a Z gamma, is a group ring module. So this is very important for us. And this is the difference between the usual K0 and the graded one. Usual one is just an abelian group. But now here, it's not only an abelian group, it has a structure of a module. So it carries a lot more information. So that's why there is a hope that that would be an invariant. Oh, okay, so we can, yeah, sure. We continue after break.
It's up to you.
Yeah,
If
sure.
it's a good place to
It's a
start.
good place.
Are there any questions for Roozbeh?
Just one question. This theorem of Grimm and so on, is it valid for division rings also? It's two fields.
Oh, that's a very good question. In fact, I found, so, right. So this is a field, right? I could construct all these just using a division ring. There is one thesis of a student, I forgot the name of the person, but it's student, I think he did not continue mathematics, and I understand why. You see in a moment. He's a student of Elliott, I think. So instead of field, he just worked with Hamiltonian over R. Not all division rings, just Hamiltonian over R. And then here, you have to add 3 more ingredients. Okay, and they are just like, it's, very ugly ones. But anyhow, he realized that you have to have these invariants, then would classify just over Hamiltonian over R. So, so it's very involved, the thesis, and that's an indication. I think it's very difficult to just move to.
Any other questions? Okay, yeah. There's a
So, so what can we say about this map? Is it injective? Do we have graded modules which are isomorphic as plane modules but not graded modules? This forgetful map of graded K theory, K0 and...
This one you mean?
Yes.
This one? Okay, in some specific cases, in fact, this is also quite interesting. In some specific cases, so how do you compare? So R should be something like regular in a non-commutative setting. Noetherian, R should be regular Noetherian, and some more conditions I have to think about. But then if that happens, then you would see that K0 graded of R divided by, so if you kill the shiftings, so I basically identify P with the shift, and this is R has to be Z graded. So you see what I'm doing? I'm killing the shifting. So P and the shift are the same. Then it happens that this is the same as K0 of R. So in this specific situation, it shows that the difference between graded K0 and K0 is just the shift. But you have to have some condition. The one I remember is it has to be Noetherian and regular so that you plug it into this long exact sequence of K groups.
Do they define K1 also, or do you study K1?
I mean, you can define higher K groups. That's not a problem. So the category of graded modules are abelian. You just plug it into the equivalence construction of higher K groups. So you have higher K groups, higher graded K groups. So you have that. But I mean, how do you use that? That's another.
Because then a question would be that given a Leavitt path algebra, if you define its K theory for higher dimension, is it periodic or
Oh, yeah.
the others K1 coincide with the other K1s in algebra?
So what periodicity?
Yes.
Right, I see where you're coming because you're comparing it with C-star.
Because if K0 is
I doubt that would be the case, but I can't tell you the answer. I doubt that would be the case.
Is there a reduced K also? Yeah.
Oh yeah, I mean you can just, this goes back to Rabaya's question yesterday about the stable rate. Yeah, so you can just get the K0 graded R and you just kill all these similar to the yeah, I mean you again you can I mean here it's just K0 is enough to classify ultramatricial. But K0 is enough. But maybe if I just relax this situation, I'm not sure. If you relax this to some other things, maybe you need K0 and K1, similar to the C-star case, maybe. I don't know.
Let's thank our speaker and resume in 10 minutes.